Thank you guys for joining me and picking up to finish this lecture from earlier today. So we were going to pick up on our indirect conversion detector. So this is indirect. We know that it is going to take a photon coming in and it is going to convert that photon into light, and then the light will be coupled with something like our amorphous silicon or our fiber optics, and it will convert or take that light into our collection element, which in this case is going to be the TFT, the thin film transistor, a CCD, which works very similarly, or a CMOS, which would be the complementary metal oxide semiconductor. Any of these three items that could serve as the collector device is going to absorb that light and convert it into an electrical signal. At this point, it's going to go and it's going to act just like basically a CR system from this point on. So here we have our electrical signal. Again, that needs to be run through an analog to digital converter. We know that we already talked about things today like our sampling frequency that's going to be really important here, like our bit depth that is going to be essential in determining our grayscale. And so all of that we've already discussed as it relates to CR and other type of image receptors is going to hold true for our indirect detectors. Now, one thing about to talk about CCDs versus CMOS. So CCDs, the charge coupling device we've talked about for years, these they're going to be very small devices. They are going to absorb light, and they are going to convert that light into an electrical signal. These have been used for some time. They are relatively expensive to make, and they do have a couple downfalls. So some of the things that can happen is if they put a lot of charge coupling devices together very close, they can actually start to function as a singular charge coupling device. And when that happens, it almost is going to act like a larger pixel and possibly affect some of your spatial resolution. The other thing that is when they start putting groups of charge coupling devices together, they can have something called seaming or tiling effect, where they actually act as a big tile, and they can leave some areas of your image that don't necessarily have data and therefore must be accommodated for by the use of interpolation during your pre-processing process. So CCDs can show tiling, lack of information due to grouping of large numbers of CCDs that act as one unit. CCDs are usually used with cesium iodide capture elements, fiber optic or lens coupling, and a CCD collection device. So it's usually those three things utilized together to make a system. CMOS, on the other hand, these work with scintillators, so it could be something like a cesium iodide, but doesn't necessarily have to be cesium iodide specifically. They're coupled with either fiber optic lenses or something new called a crystal light tube. And so these are very efficient light tubes that are making these CMOS products more prominent on the market today. And then, of course, we would still need that collection device, and the CMOS itself would act as a detective element and be the collection device of these systems. Now, for CMOS collection elements, each detection element would have its own amplifier, photodiode, so it would amplify the light. Then the photodiode would collect the light and convert it into an electrical signal. That electrical signal would be stored in the capacitor on the CMOS detection element, and then it would be surrounded by transistors, which would allow that electrical signal to be released at the appropriate time to keep it in order so that it is still in its spatial domain when it gets to your display. These are, again, very similar to your TFT devices, but they are using less power, they're more inexpensive, and they are getting better in function, and so we might see more and more of these on the market in near years. Okay, some other specific considerations on CR and indirect conversion detectors. So I mentioned this, that we can have different types of organization of our collection devices. So in the example we used this morning, I said, okay, you might have cesium iodide and they're going to be closely packed together in a big thick row, and that will help improve our DQE because that big thick row, it's going to have a higher probability of catching or capturing some of our photons. So if this was the case and we just have these kind of blob or unstructured crystals of cesium iodide or gadolinium oxysulfide, any sort of scintillating device, we would refer to that as an unstructured form of the scintillation device. If these were grown in crystals that were of like a needle-like form, then we would call that a structured device. So we notice if we have a photon come in, it hits this unstructured or blob form of, say, cesium iodide, it is going to create a more divergent light. That's going to cause a reduction in our spatial resolution. Same light, the photon comes in, hits one of these structured scintillators, it's going to produce a much narrower light, leading to less dispersion of that light and improved spatial resolution. So that's our difference between structured versus unstructured. We can see structured versus unstructured used in both computed radiography or CR as well as indirect DR. We don't see it in direct DR because we don't have any light in direct DR. Okay. Now, the thicker the layer of either structured or unstructured collection devices are going to have an increased DEQ. Or DQE, excuse me. So the thicker the layer, the more probable it is to catch the incoming photon, therefore the higher detected quantum efficiency it will have. As we have that thicker region, or especially if we have an unstructured thicker region, then we're really going to lower our spatial resolution. Okay, that brings us to direct radiology. So, so this is where we go straight from photon to electrical current. When we're using an image receptor with direct radiography, typically we're going to have amorphous selenium coating a TFT. So with this particular case, we have our TFT is going to be made of, each TFT will represent one detection element, okay, or one DEL, okay. On top of that TFT, we are going to have 1 pixel of amorphous selenium housed between or sandwiched between 2 diodes. When our photon comes in, it interacts with that amorphous selenium and it ionizes it. So we have 2 now free, a positive and a negative ion. Those ions are going to be attracted to the different diodes, and the diode that is attached to the TFT is going to take the signal of that those free ions, and that signal is going to then be is then going to be stored in the capacitor and saved as a signal representative of the number of photons that interacted at that space. So excuse me. So with direct digital radiography, we have flat panel detectors. They're typically referred to as flat panel detectors. These can be used in direct as well as indirect digital. Both of those would be known as flat panel detectors. Now, direct specifically are detectors that are going to take in those photons and convert them right into an electrical charge. So in these cases, they have the amorphous selenium, they have a signal storage or a capacitor, they have a signal readout, and then they're going to have digitizing or an ADC to integrate with the flat panel to convert that electrical signal into our digital signal. Okay, so the detector itself is going to have amorphous selenium as its capture element. We know that amorphous selenium is actually then going to take the ion, become an ion, and move through the substrate to the TFT. Therefore, it becomes the coupling charge as well, or the coupling component as well. And then it's at that TFT where it's going to absorb that charge, and that's going to be our collection element. As I mentioned, the TFT is divided into individual detection elements. Each detection element will make up 1 pixel. The smaller our detective element sizes are, the smaller our pixels will be, therefore the better our spatial resolution will be. Now, because our detection elements are not going to be 100% covered with our radio-sensitive material, we know that as the fill factor. The fill factor is the part of the TFT that is going to be sensitive to those ions. That is usually going to make up about 80 to 90% of the surface of our TFT. The other 10% or 20% that's not covered with that sensitive material is going to be covered with a capacitor or something else, and that area is not going to be sensitive to those ions and therefore miss any charges coming to that area. So because of that, we want high fill factor in order to keep our systems as efficient as possible. Here we see an example where this would be our TFT right here. This would be basically our diodes here and here, and this would be our amorphous selenium sandwiched in between those diodes. When I have amorphous selenium atoms and a photon comes in, it's going to ionize that atom, meaning it releases an electron. Electrons will be attracted to the positive diode, and the rest of the atom will now be positive because it lost an electron, and it will be attracted then down to the other diode at the TFT. So that diode then will collect those ions. Depending on how many ions are there, it will develop an electrical charge, which it will store in its capacitor until the transistors let it submit or read out the electrical charge. This is where I was mentioning today, some of these are being built now where they have their own analog to digital converter right there in the TFT, so that as soon as that signal gets stored in that capacitor, it gets processed in the ADC, and we don't have electrical signals any longer coming out. We have quantized signals coming out where there's an actual value associated, not an electrical charge. Here's an example of just the scintillation phosphor. So if this is scintillating, we know this is an indirect flat panel. It's got the scintillation phosphor. Photon would come in. It would create a light. Light would then be coupled with fiber optics or some other entity like amorphous silicon, and then that sensitive area that is filled with sensitive devices on the TFT would absorb that light, and then the TFT would convert it to electrical signal, and that electrical signal would be stored here in the capacitor until it was time to be read out, in which it would go through the transistor. Okay, so here is an example of the amorphous selenium. So a couple unique things about amorphous selenium. It's amorphous, meaning that it can be converted from a solid to a liquid. It is again sandwiched in between electrodes, which are going to pull the ions one direction or another. Selenium happens to have a fairly low atomic number. Because of this, it has to be thick or it would have a very low DQE. So selenium layer also has to have an electric field to limit the lateral spread. So it has to be attracted directly down or directly up to the diodes so that they don't spread and cause like a scatter type event. Once that amorphous selenium basically acts as the capture element, gets ionized, and then those ions move through the rest of the selenium to the TFT, that would be the coupling event. Once it hits that TFT, now we're in the collection event. The TFT is then going to measure the amount of those ions and create a representative electrical signal. Those signals get stored in the capacitor, and then that capacitor either sends it out at the appropriate time or converts it to a digital signal and then sends it out at the appropriate time. At that point, with our direct image receptor, once it's sent out and it's digitized, we are back at histogram time. So we'd be counting up these raw data grayscales, charting it on a histogram, and going from there. Okay. So direct DR, These can be utilized in a few different ways. They can be permanently mounted to the bucky or a mobile system. So they can be an IR that you pick up and you walk around with you and you put different places, or they can actually be something, a detector that's built into your table where you just lay your patient down on the table and the detector is basically built into the table. It's part of the table itself. Images are immediately available. We are finding that these do have the highest efficiency or the highest DQE when used at higher KVPs. Their spatial resolution is better than CR and probably better than indirect as well, because we're not using light, and when we use light spreads. With this, we have a direct interaction of the ion to the TFT, so we shouldn't have that spreading of signal. Spatial resolution is limited by the detection element size, and remember, detection element is really just another way to refer to your pixel size. So you know, if you have big pixels, big DELs, you're limited in your spatial resolution. If they're very small, then that would be a benefit to your resolution. The direct DRs are considered very expensive, and so that's one of the reasons a lot of people go with the indirect systems instead. Okay, the digital image, so this is going to be a lot of review. I might go a little bit more quickly through here, but regardless of what type of digital image receptor you're using, whether it be CR, DR, indirect DR, all of them, if they're digital, are going to be only as good as their spatial resolution, which is dependent on their pixel size. All of them, all three of them, as soon as you have gotten them to the point of an electrical signal, all three of them have to use an analog to digital converter. That is only going to be as good as the bit depth that converter utilizes and the sampling frequency it applies. Okay. At this point, that analog to digital converter, again, must, in order to maintain Nyquist frequency, it must sample the signal at least 2 times per cycle to be accurate, and then it must quantize or create a digital value, a discrete digital value signal. And that digital value signal is then going to be counted up and plotted on a histogram. But it's also going to be maintained in order. So it doesn't just end up, if it was, if it occurred in the upper right lung, we don't want that signal to appear on our image in the lower left lung. So it is going to have to follow its spatial domain, stay organized, get plotted on this histogram, and yet still end up with that gray signal in the appropriate digital placement on the display. The digitized pixels are intensities. They are patterned across the computer screen to form the matrix. Remember, the bigger the matrix, the smaller the pixels, the better the spatial resolution. Each pixel has its own brightness level, and it only gets 1 brightness level per pixel. You can't split a pixel in half. It is what it is. So as soon as we have that quantization, that pixel is going to be that shade of gray and no other for the particular image. Okay, for all of our digital imaging systems, after that analog to digital converter, we have to go into the pre-processing stage. So this is where our histograms start. So first thing our computer system is going to do is going to see all of those quantized digital values coming out, and it's going to start plotting them on the raw data histogram. Okay. At this point, after it gets to the raw data histogram, then it's really going to start to go through those pre-processes. So the first thing that it's going to do is it's going to apply the field of view recognition, or also, I'm trying to think of the other term they can use for it. But basically, it's going to say, okay, you selected a hand on my workstation. A field of view for a hand usually starts at this brightness level and ends at this brightness level. And that's going to be therefore my S-min and my S-max. And halfway between the two is my S-average. It gets rid of that extra information in my field of view recognition that should not be considered part of the histogram anymore. Okay. The next step is that it is going to pull the perfect histogram out of the deep entities of the computer. It's going to pull that perfect histogram up, and it's going to basically superimpose it over our raw data histogram. This perfect histogram, remember, is called our lookup table. So now our lookup table may be close to our histogram, may be a long ways away. The closer it is, the better. and it's going to be superimposed here. And our raw data histogram is then going to be, if this is my S average of my lookup table, my raw data histogram is going to be shifted so its S average aligns with my lookup table S average. And the difference between the two, the lookup table S average and the raw data S average, is going to show the deviation index from the perfect target exposure. So if my lookup table SAV was my perfect target exposure, let's say on our system of 800, and this one was 600, my deviation index would have been 200. Having to move from 600 to 800 was a deviation of 200. Okay. In that process of overlapping that lookup table and then shifting the raw data to match the lookup table histogram, that process would be called rescaling. Okay. So the histogram analysis, the image processing, identifies the edges of the image. That's your field of view evaluation. It compares it to a pre-established histogram, the lookup table, specific to the part to be image. All digital images have the ability to evaluate original image data, that's our raw data, and then assess it according to histogram analysis. Histograms are simply a plot of the frequency of particular grays. Okay, so that's the basics of our histograms. We know that each individual image is going to have a slightly different histogram because each patient is going to have slightly different attenuation qualities, and our technique's not always going to be exactly the same, and there's just a multitude of factors that could affect a histogram. So each image has its own distribution of values of pixels, meaning that some may have a whole lot of brights, some may have very few grays and very few blacks. Others may be completely opposite, very few brights, a whole lot of grays, a whole lot of blacks. Every one of them is going to be different. And what the histogram looks like depends on what came out of that analog to digital converter, the values that these discrete digital readings represent. Okay, so radiographers, we must select the proper lookup table histogram. That means we do that by selecting that on our workstation. So when we go in and we select our patient, we know we're going to do a PA chest x-ray. We need to make sure on our workstation we select the little guy with the PA chest x-ray. That doesn't mean that we go to our console and select the PA chest x-ray on our technique. We can manually technique that. We don't need that. It means on our workstation on the computer, we select the appropriate anatomic image. Computer, like we said, is going to take our raw data histogram, match it with our lookup table, and then do processing algorithms to compare and superimpose and rescale them. The volume of interest is like the field of view recognition, so that's just recognizing what area is the volume of interest, putting those S-min, S-max applied to the raw data, and then wiping away what was extra that should not be included on the exam. Each histogram will have its own unique shape, and then when we superimpose it with the lookup table, it will try to kind of morph itself towards that lookup table shape. And that, again, is called automatic rescaling. So here's just an example. This is a chest x-ray. This is the particular, let's say that this is the raw data histogram for this chest x-ray. The volume of interest, or the field of view recognition, is setting the S-min here, the S-max here. So it's getting rid of all of this information, and it's showing that we have very few, if this is our numbers over here, very few shades of very bright gray, a lot of shades of mid-level gray, and very few shades of dark gray. Okay. Now, if we shift this and we try to use this particular histogram as my lookup table, and I shift my image, this histogram, I superimpose over this histogram, and it shifts it to match this, you'll see that I have a very high level of blacks now, very low levels of dark grays. Oh, excuse me, a very high level of brights. I have to look at my scale here, brights. Very high level of brights, very low level of light grays, and a very high level of dark grays. This is a slightly different histogram where you see that I've got a lot of dark blacks, a lot of medium blacks, and then just a few spikes of bright whites at different shades. Here I have a lot of bright whites, as you can see. It correlates here. Very few low-level grays, some dark grays. So you can go through those and you can kind of look at the individual and how really just applying those different histograms is gonna change the overall appearance of the image. Histogram errors, this is where we talked about in class, like, okay, sure, you might want to look like what's her name, Megan Fox, and for some people that might be really easy to do. They kind of look like her already. No problem. That's like matching a good raw data histogram with the lookup table, and they just squish together and they look exactly alike. Now, other times you may look the complete 100% opposite of Megan Fox, and no matter what you do, no matter how you try to look like her, it is not going to mesh, and the gap, the change is going to be too big. That's what happens when we have a histogram analysis error. It means our raw data histogram looks nothing like our lookup table, and therefore, as much as it tries to morph itself, it can't get the job done. So in this particular case, we'll call that a histogram error. So in CR, in computed radiography with our reader, if the entire imaging plate is scanned to track to get the image from the PSP. If at least 3 edges are not identified, a histogram error can occur. So it needs to be able to, we have to be really careful because of this with CR imaging that we are going to collimate equally on all 4 sides. Otherwise, it has trouble identifying the volume of interest. And so it can cause really significant challenges with your histogram error. So in this particular case, you can see this guy is easily collimated pretty equally on all 4 borders. This one is open all the way to the top, but collimated here. And so it's got big collimation here, here, and here, no collimation up here. Because of that, it's getting a histogram error. And despite the technique being just fine, you can't see anything on the image. So that's why we have to avoid histogram errors. Okay, histogram analysis maintains consistent image brightness despite over or under exposure. So using histogram analysis or using a lookup table, it says, hey, I've got that optimum lookup table histogram right here. You are a little bit underexposed. You kind of look like this. I'm going to shift you so you meet my lookup table, and I can kind of correct for some of that. You are a little bit higher exposed, and so I'm going to shift you towards my lookup table, and you're going to look a little bit better. So we have 3 very different technical images here, but because they can be shifted and rescaled to match the lookup table histogram, it can make them much more consistent. Okay, so some of the things that we watch out for on histogram, like I talked about, the importance of that S average. S average on your lookup table is the perfect exposure. It means you use the perfect technique. Your raw data is always going to be compared to the lookup table. Your S average is always going to be compared to the lookup table. If they're not the same, you did not use the exact perfect technique. Okay, if your exposure index is going to describe whether you are underexposed from the lookup table or overexposed compared to the lookup table. Okay, the farther over or underexposed you are, the farther you're going to be from the target. Okay. The amount of space that the rescaling process had to move your raw data histogram to match up with the lookup table histogram S average, that's going to be the deviation index, or how much it deviated from where you wanted to be. We always want to keep our exposure index within the normal range. If it's outside of the normal range and our image still looks really good and it's just barely outside, you might still have a case for not repeating that. If it's way outside or if it doesn't look good, you have to repeat it based on that. Optimal ranges are specific to each vendor, and unfortunately they make this as confusing as they possibly can. So vendors like Fuji and Konica, I think they actually have merged, so it's kind of the same vendor. They use something called an S value. Now with this, when I have a high S value, so a target S value on Fuji and Konica is usually about 200. And if I have an S value that's say 600, You might think that that's overexposure. Well, for Fuji and Konica, they have an indirect relationship or an inverse relationship, meaning the higher this number is, the more underexposed you are. Okay. Now, Carestream is totally different. Carestream uses an exposure index, kind of like our system in our lab does. We know our system in our lab has a target of 800. It says between 600 and 1200, that's within target. If you're over 1200, you're overexposed. That's a direct response. Over the value means overexposed. Now, when we go back to this S value on the Fuji and Konica, over the value actually meant underexposed. Inverse or indirect, whereas Carestream in our EI is direct. Okay, AGFA is the same thing. It uses IgM log median value, and their average is about 2.5. If you go up to 2.8, that's fine. If you go down to 2.2, that's fine. If you're over 2.8, you're overexposed. So this would be a direct relationship system. They've been talking for a decade about how they need all of these systems to report the same way, and they still aren't doing that. Deviation index, like I said, exposure index is telling you if my exposure target is 800 and you got 600, that was your exposure index. It shows me, hey, my exposure was a little bit low. Deviation index is basically saying, hey, not that it's a little bit low, hey, you're 200 low. You're deviated from the target by about 200. Okay, so a deviation index of 0 would indicate that it's perfect. You got 800, you're right on the target. Anything above that means I'm overexposed. Anything below that means I'm underexposed. Exposure index and deviation index limitations, sometimes they can be limited by collimation, either over or under collimating, can mess up the histogram evaluation of your S average a little bit. Really high or really low KVP can do the same. Centering inaccuracies or choosing the wrong anatomic part on the workstation, those can affect your EI and DI. Inaccurate data extraction or computer rescaling, so basically a histogram error can affect these. And then a lot of noise, either quantum model or scatter, can affect these values. Lookup tables I talked about quite a bit. That is that perfect table that exists in the bowels of your computer system that says, hey, this is the histogram of the perfect hand or the perfect abdomen. They utilize these lookup tables then to manage our raw data histogram to try and convert them for consistency or rescale them for consistency. Here's just a couple examples. If I took an image that was very, very low contrast and I matched it up with my lookup table, and my lookup table was like, hey, your 40s look like this and your 30s look like this, but you shouldn't have any 40s and 30s. You should have 90s and 10s. So it would run through this perfect lookup table and it would convert those 40s to 90s and the 30s to 10s, and your ultimate image would look like this. I honestly, this is how Fauber describes it, and some of you might prefer this approach. I really do prefer how it is described more in our McQuillan, where you're superimposing those two, the raw data and the lookup data, and you're kind of trying to align them and match them up, and that's where you get your rescaling done. Okay, so this is just a couple more visuals of how those lookup tables kind of can affect an image. Okay, digital imaging artifacts. So there can be many different causes of digital imaging artifacts. Some can be very prominent, others can be very subtle. A lot of them, good news or bad news, depending on how you look at it, are not going to be able to be corrected by us. Okay, so it's no longer like, hey, open your film cassette and wipe it off to get rid of any dust that's in here causing these artifacts. Now we have these sealed electrical flat flat panel detectors, we can't be opening them and messing with those electronics. And a lot of the time that's the issue. So our artifacts on our digital imaging systems are often due to electronics. They can be classified in a few different ways. First, it could be classified as prior to the ADC. That would mean that there was an issue with my capture, coupling, or collecting device, or the capacitor in my TFT, or the bus lines from my TFT to my ADC. The next problem could be during the ADC. My ADC is not functioning properly, probably going to mess up my grayscale somehow. Or it could be after my ADC. This could be something that would have to do with the histogram or the transport, maybe again, those bus lines from the ADC to the actual computer processing system. And then finally, if it's getting pre-processed and pre-processed, okay, but there's something issue with my display, that would be a display artifact. So it could happen and be classified depending on where it happened. It would be classified into one of those categories. So some examples that we can see in CR, there might be some that we can actually address. So particulates within the CR cassette, because our CR cassette opens when it's in the reader, dust can fall in there, you can get a scratch, something like that. Those can be cleaned by technologists. That might be something we actually have control over. Cracks and fogging, we don't have control. Well, fogging might be because I left my CR out while I took my lateral chest after I took a PA test on it. Now I have fog all over it. That could be something that I could run it through and clear it. So with CR, there is a little bit more tech involvement with clearing artifacts. When we get to indirect and direct DR, there's very limited involvement. So usually these are addressed by calibration of the detection elements. Sometimes that can be by putting through an offset electrical charge that kind of clears any stored up electrical charge in the system. It can have rows or columns that need to be cleared of electrical charge. It could be caused by electrical readout malfunctions or electrical components of the ADC. So as you see, it's probably for these, it's really going to be a specialist, an electrical specialist, or some other specialist that's going to be able to correct these if they can. Okay, our image display, as we talked about, our soft copy viewing, you know, that's any time we're viewing an image on a computer, like in this example. Hard copy is when we hold that image in our hand like a film. Okay. The performance of the display monitor, as we talked about last week, is very, very important. Luminescence, resolution, and ambient lighting, those are all essential when you're setting up a radiologist reading room. We need to look at illumination and lumination as separate entities. We know that the resolution is very important on the display monitors so that they're not going to be missing things with high subject frequency. Primary displays are the ones that the actual diagnose are going to be made off of, so those have to have the best qualities. Those are the ones in the radiologist reading room. We are considered secondary at our workstations. Okay, we talked about display monitors last week, so this can be kind of brief, but we can have cathode ray tubes, which we'll look at here in a second, but they create an image by having the front screen is covered in graphite with a phosphorescent material behind that graphite. It uses an electron gun where electrical current comes into that electron gun. Charged coils are going to direct the electrons to one area of the screen. It's going to shoot electrons to that screen in a raster pattern, left to right, and then interlace it top to bottom at the rate of 30 frames per second. All right, this creates an image, and that is basically the basics of the older cathode ray tubes. Now we're typically using liquid crystal displays, and remember, these are going to have we're looking at from the side, this is my LED backlighting. Here is my TFT, and anterior to that TFT, we are going to have our sandwiched area where we have, if I zoom in here, we have a sandwiched area where we have two diodes, and then we have liquid crystals with their dipolar charge, with a positive at one end and negative at the other. Depending on the charge that gets to my TFT, it's going to cause them to align and then allow this backlighting from the LED through. Plasma monitors are very similar to our LCDs, but rather than having liquid crystal diodes like we have right here, or excuse me, we would have basically 2 diodes, and we would have gases in between those diodes, and when the TFT provided the charges, the gas would produce a different wavelength of color. So here's an example of an older, not real old, but an older cathode ray tube. You see that it has that thickness in the back where the electron gun is going to be. It has that graphite screen, and it's basically creating a phosphorus glow on that graphite screen, and that's what we're seeing. Here, we know that this is covered in liquid crystal pixels. There it has a white backlighting, and then we're aligning those liquid crystals in order to allow that light through. And so here's that comparison of the two separate, the cathode ray and the liquid crystal display. Okay, placement of displayed monitors and ambient lighting, like we talked about last week in Bouchon, that is going to be very important in that it affects how the radiologist can read those soft copy images. The monitor matrix should be at least as large as the image matrix size. Remember, our system is only as strong as its weakest link. So if I have a poor display, I don't know, 50 by 50 matrix on my display, but I am producing images that are 2000 by 2000 pixels, I'm only going to see the 50 by 50. So our system's only as strong as the weakest link. Our display image should be as big or greater in matrix size than our image receptor. Monitors have to have a high luminescence ratio, or they have to have high luminescence or luminance, because we know that we need additional luminance, or the higher luminance allows us to see subtle contrast or higher contrast resolution, and so we need to have that good backlighting. Pixel depth is going to affect our contrast. That's in our ADC. Monitors with higher luminance can display greater grayscale, and visualization can be affected by spatial resolution, luminance, and contrast resolution. And that spatial resolution and contrast resolution are going to contribute to the MTF, right? So the better our spatial, the better our contrast, the closer to 1 we are on our scale of MTF. Okay, we looked at these last week, so there's not going to be a whole lot more on them, but remember, the original pattern that we saw, and you can see right here, was the SMPTE, Society of Motion Pictures and Television. That was the SMPTE pattern. That was the original pattern that they would use to assess the function of a display. We've moved away from that, and now we're using AAPM. And remember, it's the AAPM task group 18 that is commonly used now. And there are a number, I can't remember exactly what the number is, but there is a number of different, in that task group 18, there's a number of different patterns that you can use. Those patterns are all going to come with instructions of exactly how to evaluate them, and so it can make it a pretty easy project if you're willing to read the instructions. Okay. So these patterns can test for geometric distortion. So things like this, looking for barreling, we can take our measurement tool out and we can measure and make sure that our squares are the same size here as they are here or here or here. We can look for pin cushioning, doing the same thing with those squares. Look for luminance, so we can use a photometer to take specific measurements of our grayscales. We can look at contrast resolution, make sure that we can make out all these different shades of gray. We can look for noise, so looking at patterns and seeing if noise is covering up subtle little things that we should be able to see. We can also look for veiling glare, which would be kind of a scatter across the image, or we can look for specular or diffuse deflectors, all of those things that we discussed last week. Okay, pre-processing is really that process of our use of our histogram, but then it is going to incorporate things that we talked about last week, like flap fielding, interpolation, anything that occurs before we actually see the image. Post-processing occurs after we see the image. So there's software options that they allow us to manipulate the image. So this would be windowing, it would be leveling, it would be electronic masking, which I don't want to see you doing, right? Here you see a person that has actually done a pretty decent job electronic masking. They brought the mask right to the edge of the image, but they didn't cover up any anatomy. That's fine. When you start covering up anatomy, that is absolutely not fine. That is an ethical choice that can result in damages to the patient if you choose to cover up something that you exposed. So not okay to electronic mask. unless it's just to cut off an unexposed area. Windows and levels, we can window and level. Let's say I windowed and leveled to see if this was really a good image or not. I have to reset it back to the raw data so that I do not lock the doctor into my window and level settings. Level is going to be setting the brightness. Window is going to be accessing the number of shades of gray. So long grayscale, short grayscale, that's window. Level is the level of brightness. Okay, so here's just window and level, kind of showing you that. Here's more window and level. I'll let you take a look at that. Other post-processing techniques, subtraction. This is something that is done usually in surgery, where we're going to talk a little bit more about this when we get to interventional radiology, but it's the removal of superimposed structures so an anatomic area becomes more visible. So subtraction, it can be done, here's something like a heart. Let's say we were imaging the heart and then the doctor injected contrast, but now he wants to go through that vessel with contrast with just his catheter. So he could subtract the contrast and leave a roadmap where he could advance the catheter. And we'll talk more about that. Contrast enhancement, that is where it can alter the pixels to increase or enhance certain levels of gray. Edge enhancement, also kind of called high bandpass filtering. It would be like an AI process where it would assess the image looking for sharp delineations of signal. So maybe a really low signal against a really high signal that would indicate there's an edge there, and then it would continue to even enhance that edge more. Inversion would basically be flipping the images so your blacks turn white, your whites turn black, and so on and so forth. Smoothing suppresses noise, so it's really adding interpolation or averaging pixels to fill in where missing pixels might be. It smooths the image, but it allows for some noise, or a decrease, excuse me, it allows for some decrease in spatial resolution. Equalization is, this is kind of like flat fielding. So it can find where there's some underexposed areas and kind of try to make them a little bit darker to create a more balanced image. Region of interest, that's where we can take a little detector, put it over a little part, and it'll give us a density reading that may correlate to a specific anatomic material, blood, urine, bone, something like that. And then stitching is what we use when, we used to, if we were doing a scoliosis series, we would go from all the way C-spine all the way through the pelvis. Now we don't have IRs that are that long anymore. And so what we do is we take it in 3 separate entities, and then we can use these things like post-process stitching to look for anatomic areas and stitch it together so it looks like one long image. So here's an example of subtraction where they picked a basic density and they had it pull all density of that grayscale off. Here's edge enhancement, how you can see it kind of makes it pop on the edges. Here's smoothing, where we're kind of looking a little quantum modeling, so it comes in here and it averages those pixels and fills in the gaps, but again, it takes away that spatial resolution. And here is equalization, where you can see they recognize this was very bright, and so it did flat fielding to kind of equal that out. And I think we have been over DICOM, HIS, RIS, HL7, PACS, all of that a number of times. So I'll let you reread this, and I will let you guys go for the day. So thank you for making it through this extra long lecture with me. Have a great day. Bye.